Okay, so let's continue on in the 1D world. So let me remind you briefly what we did yesterday. So yesterday we tried to solve the very simple quote problem, which is the Luttinger model, which is simple bosons, not even fermions for the moment, but bosons with a kinetic energy and then on-site repulsion. But of course, this is a very complicated problem because again, you get 10 to the 23 particles which are interacting together. And what we did was for the moment just to do a change of variable and to say that we can represent the density as using an auxiliary variable, which I call phi, which is the kind of deviation from this field phi L to a straight line, which is here. And using this and doing a certain number of transformations, you can rewrite the density as the average density minus a gradient term of phi, and then sort of a sum over harmonics. And we discussed this last time. Each one of these terms has a kind of different physical significance, which corresponds to a sort of Fourier transform of the density that you can visualize very well by assuming that phi is practically constant. Of course, phi is an operator, so it does what it wants, but imagine that phi is 0 for the moment, or phi is a constant. So if phi was a constant, this term would just be rho 0. But if now phi is varied super smoothly at the scale of the lattice, you see that it would correspond to bringing more density or taking it out of a given point. Point to be viewed is in the hydrodynamic sense, meaning many, many sites, but let's say a localized region in space. So this term takes care of bringing more particles, and indeed that's the divergence of phi. But this term is not telling you that at a very precise position in space, you might have shifted the particles. Because this term, if phi is varying slowly at the scale of the lattice, is something which is an hydrodynamic description. What is taking care of this are the other terms. And you see that the other terms are the higher harmonics. So you know that by piling up harmonics, you can transform sine into delta functions, are all the harmonics of something which has exactly the periodicity of one particle per site. This is exactly what you have here. But then, because I have a phase here, I can shift the maxima. So I can put my peaks everywhere I want. And of course, the implicit assumption is that if phi is smooth, then I cannot do it really crazily. I cannot take these two peaks and put them together. If I want to do this, phi will not be smooth because it varies at a length scale which is short compared to the lattice spacing. But if phi is smooth, it means I can still shift my peaks, but I will do it everywhere, let's say within a certain circle around a given point, and then I can shift them differently here and shift them differently here. So we can do an hydrodynamic description, but note that the density operator can be extremely discontinuous still, because if the peaks are shifted, and if I put all the harmonics, then density is 0 here and infinite there. So by making this density operator written in a much more complex form than initially, I can have now the possibility to keep phi smooth while retaining the extremely singular nature of the density operator. So it's a trade-off. Either I write it simply in terms of fields, but the fields go crazy, or I decide that I want only to have smooth field, and then I must put the complexity in the form of the operator itself. And that's what is done by this beautiful formula. It can be extended to a higher dimension, but only for crystals that we were discussing. And to complete the change of variable, I need to know how to write a single boson operator. And this is very easy, because B dagger B is the density. The single boson operator is kind of the square root of the density, which I can write here. And then I have to remember that this is a complex operator, so I have to put a phase. So the phase is clearly another operator. If I was in a superfluid, this would just be a number. But here, it has no reason to be a number. It's an operator. Okay. So we have these two fields, phi and theta. And we need to now use these new fields instead of the B and B dagger, instead of the original or position and momentum of each one of the particle and so on, to rewrite the Hamiltonian. So let's try to do it. The first thing is there a relation between phi and theta? And for that, trust me, I don't want to do the calculation, but if you say that no, it's not too complicated, but it takes time, and I think there are more interesting things to do. If you say that b of x and b dagger of x prime are commuting, so they satisfy the canonical commutation relation of bosons. Sorry, there is no I, of course. They satisfy the canonical commutation relation of bosons. And again, you will see this commutation relation in the second quantization course that will be done in the course by Misha. Then you can, I would say you can satisfy this. Let me write the arrow in the other direction. You can satisfy this if you impose that the field phi of x and the field theta of x are not independent, but that you have that phi of x and 1 over pi grad theta of x prime are obeying the commutation relation I delta of x minus x prime. It's not complicated. Take these formulas. You have it in the book that I was referring to. By the way, I gave the copy to the library, so if you want to have a look, you will find it in the library. Write bx, b dagger, minus b dagger b. Beware that if you try to pass operator through one another, then you will have to use the commutation relation. And if you work out that, you will find that you satisfy the commutation relation of the b. So this is a remarkable formula because it tells you that this is the momentum conjugate to the field phi. So in a way, I can view that as position and momentum, if you want, in some abstract space. And grad theta is actually the momentum which is conjugate to the field phi, which is nice, as you will see in a moment. And again, physically, it means that if you have a superfluid or if you have a superconductor, it's a well-known fact since BCS or since Phil Anderson noticed it in BCS, that if you fix the number of particles, then the phase of the wave function is fluctuating a lot. If on the contrary you fix the phase, you can only do it if you let the number of particles fluctuate a lot. So this is a well-known duality or uncertainty principle that you have for any function that breaks the phase symmetry, that the number of particles and the phase are kind of conjugate variable. Here you can put it on a relatively firm basis because you make it an operator identity. Okay, so this is very nice, but is it useful? Now, let me try to rewrite the Hamiltonian. Remember, this is a complicated Hamiltonian. We don't know how to solve it in the boson language. So now let's rewrite the Hamiltonian. Using phi of x and theta of x, or pi phi of x, if you prefer. It's the same. I mean, if I put theta, I put phi. Okay, so let's do the two parts. And let me do first the kinetic energy. So the kinetic energy is p squared over 2m, and I have to sum over the particles. So if I use the field theory representation, and I say I have an operator which is describing the creation or the destruction of a boson, the kinetic energy will become the integral over all space of the gradient of psi. The momentum, if you apply it to the wave function, it's h bar over I gradient of the thing. So the momentum will be, the thing will be grad b dagger grad b 1 over 2m. Sometimes people use psi instead of b, but I will keep b for the moment. So of course this is a function of x. This is a function of x. And so this is my kinetic energy. This is, again, this is keeping in mind that the momentum is essentially, let's say, proportional to the gradient applied to the wave function. So p times psi is the gradient applied to psi. So this is my kinetic energy. But now we have the expression of b in terms of the fields. So let's use the fact that b is rho of x to the power 1/2 exponential of, and I forgot if I put plus or minus, but at that stage it's not really important. Well, it's important if you want to do clean calculation, but for the derivation on the board, it's not really important. And so let's go for it. So I could go and say that the gradient of B is the gradient of rho to the 1/2 exponential of I theta plus rho to the 1/2 exponential of I theta E grad theta. That easy. And of course, the gradient of B dagger is the same thing, gradient of rho to the 1/2 exponential of minus I theta minus rho to the 1/2 exponential of minus I theta I grad theta. So if now I compute grad B dagger grad B, what I will get is something, the phase you see cancel, and I will get a grad rho to the 1/2 square plus rho, the phase cancel, and I will get grad theta square. Okay, so this is what I would get here. Now I can rewrite grad to the 1/2 as grad rho and whatever, so let me rewrite it. So this is 1/2. So this is 1/2 of rho to the 1/2 grad rho square plus rho. This is function of x a priori, grad theta square. This is also a function of x. Now I can rewrite this as 1/4 rho grad rho square plus rho of x grad theta square. Okay, very nice. I have my expression. It's not even too complicated. So this is my kinetic energy. Now, rho itself is a nightmare. Okay? Rho is this horrible, horrible, horrible expression. But what I need is not this expression here, but what I need for the kinetic energy is the integral over dx of this. 1/4 rho grad rho square plus rho of x grad theta square. So now I will start to do approximations, and you can shout at me that you're not happy with the approximations. And I'll try to justify it later in a more reasonable way, but I'll already, of course, try to make you believe that the approximations are reasonable, but don't hesitate to shout. I mean, if you have complaints, voice them. Because it's interesting, because there is a lot of reason for what I'm telling you will not work, or should not work, or could not have worked. It works. But, okay. So now let me think a little bit. Phi, I want phi to be a slowly varying function. What does it mean? It means that the variation of phi at the length of the lattice spacing is very small. Phi can be considered a constant when x varies by a, which means this thing will oscillate a lot while phi stays a constant. So I can consider that while this thing has oscillated 25 times, phi is a constant. Okay? And remember that the integral of a cosine is essentially 0. So if I have a smooth function which is multiplied by a rapidly oscillating function, there is even a math theorem that if the oscillation gets very, very fast, the integral goes away. So we'll throw away everything that oscillates. And of course, it's only true if phi is varying slowly. So I'll throw away everything that oscillates, which means what? Which means that in this gradient of rho here, the only term that will stay, okay, gradient of rho 0 goes away. That's for sure. Where is it? Gradient of rho 0 go away. Every time p will be different from 0, I will get an oscillation. So I throw away. So the only terms that remain is 1/pi grad phi. So for this particular calculation, not in general, but for this particular calculation, I can consider that actually that rho of x is roughly minus 1/pi grad phi plus oscillating. Okay, so it means that the grad of rho is minus 1 over pi grad square phi. Now, what do I do with the rho at the denominator? I'll simplify it drastically. I'll say it's the average density, rho 0. And everything else is more gradients, more oscillations, more stuff. So the first term, I will consider that this is sum over dx 1 over 4 rho 0 grad square phi, and there is a pi square here which is probably floating around. Simpler, huh? And again, if you're not happy with that, shout. The second term, same thing. I will say, let me keep the thing which has the least gradient, the least derivative, the least operator. Rho of x is rho 0. After all, there is this term, that's for sure. Whether the additional terms are important, we can think again. So I could say that this Hamiltonian is rho 0 grad theta square here, and plus terms which are grad phi, grad theta square, oscillating, blah, blah. Okay, let me throw all this. If for people who are familiar with RG, their dimension in the RG is higher. So you can say this term will be irrelevant. I throw them away. They are less, they are more derivative. When I integrate derivatives, it goes away at the end. Okay. Again, if you're not happy, that's perfectly your right. Now, if I was stopping there, it's already nice, no? Because this thing here is pi, the number, times pi, the operator, which is the momentum conjugate to phi. So what I have here is an harmonic oscillator Hamiltonian. So it's quadratic, no problem. It was quadratic in the bosons to start with. So I'd better be able to solve it, otherwise I'm bad. But I want to emphasize that if I do Fourier transform here, I can rewrite this Hamiltonian as sum over k of 1 over 4 pi square rho 0. Second derivative gives me k square, so square gives me k to the 4. Sorry, k to the 4. Then this is phi star k, phi k. And this term here will give me rho 0, and then pi square if you want. And this is pi star k, pi k. So what I have here is an Hamiltonian in k space where each k mode is represented by an harmonic oscillator Hamiltonian, except the coefficient in the harmonic oscillator depends explicitly on k. So for each mode, k, I will have a different frequency, which is proportional to k square. Now, am I happy with this? Well, if you think about it, this is the momentum. So this is essentially the time derivative of phi. Momentum is velocity, if you want, up to factors. So this term, if I was going to frequency, is omega square. It's the energy. Omega square is k4, which means omega is k square. This is my dispersion relation of my bosons. Their energy is k square over 2m. So I completely reproduce with this language what I know for the bosons. They have an energy which is proportional to k to k square. But the important thing is that this is an harmonic oscillator Hamiltonian, so I know exactly how to solve. I can represent phi and pi as linear combination of A and A dagger, and blah, 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 and I rewrite it as sum over k of blah, 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 omega k, A dagger k, A k, and I know how to solve. You just take your textbook cointanuji and or your favorite quantum mechanics book. For me, it's cointanuji. But you solve the harmonic oscillator problem, k value by k value. Yes, there was a question. Yeah, but at the end, I will only have the gradient of rho. So you're right. I can write this, of course. Yeah, it's absolutely right. Well, the only thing I wanted to say is that at the end, in the gradient, I don't care about rho zero. Rho zero is a constant, so it's differentiated. Of course, in the denominator, I replace rho by rho zero. You're absolutely right. I throw away all the harmonics except p equals 0. Yes? Sorry? It's a field. No, no. So even there, it's a field. It's a field theory that I'm writing. I'm just saying this field theory, these are operators. So this is an operator. This is an operator. These two operators are canonically conjugate. And then I have a field theory which is written in terms of two operators, phi and pi. And I need to solve this field theory. But because this field theory, just a second, because this field theory in K space decouples K value by K value, each one of the field is an harmonic, can be described in terms of harmonic oscillator. So the phi and the theta are always operator, and you have to treat them as operators. Yes. No, at that stage, no. You don't have to worry about this. Again, if I want to do the calculation a little bit in detail, it takes a little bit of time, so I refer you to the book for that, for example, or to the lecture notes that I was mentioning. But at that stage, you don't have to worry. Another way you can do it if you want to be safe in your mind is to do it in the framework of path integral, because then you can replace the operator by numbers, by real fields, and then you don't have to worry about this. Then you can ignore the commutation. But yeah, but you're absolutely right that one has in principle to worry about this, but you can do the calculation here also with operator and check that the cross term do not appear. But again, you're right in asking these questions, and they are excellent questions. It's just that if I wanted to go through every step of the calculation, I would need a couple of more lectures to carry you through in details. And so I refer you to the chapter 3 of the book on 1D that I was mentioning, where this is done in more details, or an alternative derivation in chapter 2, where you can also find this derivation done in great details. Yes, it is.
Because you squared
Yes.
the terms.
Yes.
So if you take p and minus p,
They cancel and they are not oscillating.
yes.
Heh. And so what? So let's continue and come back to the so what. So what was from 70s to 80s. And then came Duncan Haldane, who took care of the so what. So I'll come back to that. That's, of course, a very good point. I cheated you shamelessly when I say the oscillating term disappear. Yes, oscillating term with the integral, you could say they disappear, but of course, as he's pointed out, there are terms who are not oscillating. So what should I do with them? But first, let's see this solution. Let's go and try to solve, because this is just the kinetic energy. I've done tremendous efforts for the moment to reproduce something I know, that for free bosons, the energy is k squared. You could say, is it worth 2 hours of my time? I don't know, or your time rather. I don't know. But now let's look at the interaction. Okay? So the interaction was, of course, the difficult part. This was the integral over dx prime of v of x minus x prime, which I remind you is essentially a delta function, rho of x prime. This is the interaction, okay, u over 2 or something like this, if I want to put it. And because it's a delta function, I can kind of rewrite it as u over 2 sum over dx rho of x square, because it's my delta function. I think I call it g initially, which is probably more correct. I'll stick to g for the notations, but it's not really important at that stage. Now, this was the problem in the original boson language. because this is a term which contains 4 boson operators. Of course, as any interaction, I can write it with rho, or I can take care of the chemical potential term. So let me rewrite it here as rho of x minus the average density times rho of x prime minus the average density, because the rest is chemical potentials, just correcting the chemical potential. So here I call it delta rho square here. And this is 4 boson operator. And 4 boson operator, we don't know what to do with them. But now let's use our little magic formula. That rho is actually rho 0 minus 1 over pi grad phi plus oscillating, which means that the interaction term is g over 2 sum over dx of 1 over pi square grad phi square. Still a quadratic term. So my Hamiltonian is still an harmonic oscillator Hamiltonian. Problem solved. Period. I just solved for you the Luttinger model. That's it. Finished. Any interaction, anything, provided everything I said before is correct, of course. And that's it. My full Hamiltonian, H, is something which I can write as integral over dx rho 0 pi square pi phi star. Okay, let's do it in okay, I'll do it in space, but then we'll go to square plus this term, which is g over 2 pi grad phi square. And then there is a term which was the term I originally wrote, which is the 1 over 4 pi square rho 0, 1 over 4 pi square rho 0 grad square phi square. And if I go to k space, this is the sum over k of rho 0 pi square pi star k pi k plus g over 2 pi k square phi star k. Okay, maybe I can push it a little bit here. Phi star k phi k plus this term, which we said is k to the 4 divided by 4 pi square rho 0. And now you see that I don't care about interaction. They just are part of a quadratic Hamiltonian. It sounds like a magic trick. This Hamiltonian that was impossible to solve, or let's say it took better than that. It took Elliott-Lib to solve it. And believe me, it's like taking a bazooka to solve a problem. This is written as a sum of harmonic oscillators. And again, keep in mind that this is the velocity square. So this is the time derivative of the phi, if you want. The momentum conjugate to phi is roughly dt phi, which means it says that the energy here square is proportional to 1 over rho 0 pi square times g k square divided by 2 pi plus k to the 4 divided by 4 pi square rho 0. Now if you look at what this is E of k. At small k, you see that in the absence of interactions, at small k, the linear term is not, this term is not there. And I start as k square, which was my free bosons. But as soon as I will have interactions, the linear term will be there. I say linear because E square is k square, which means that the energy now becomes proportional to k, so I change drastically the spectrum. So I get something which is essentially linear. And then if k becomes too large compared to interaction, I go back essentially to the quadratic part of the spectrum. So I invite you to compare this when you will get the Bogolyubov approximation to what you get out of the Bogolyubov approximation. This is exactly the same spectrum. And you see that we got something which is remarkable, which is that as soon as we get interaction, the nature of the excitation changes. At small k, I can even throw away this, I don't care. So I wrote this term for niceness, let's say, but at the end I will throw it away, I don't care. And at small k, I have an energy spectrum which is like a Dirac spectrum where the energy of the excitation is proportional to k. If you are in higher dimension, you obtain this out of the Bogoliubov approximation, and you assume that you have a condensate. What I just show you here is, first, for me, if you forget my oscillating terms, this is not an approximation. This is my full solution. So I don't have to assume there is a condensate or no condensate or whatever. I will compute if there is a condensate or not. Because now my Hamiltonian is completely diagonalized. I just have to do the pi as linear combination of A dagger, the phi as linear combination of A dagger, as you did with X and P in, again, quantum mechanics, and I'll diagonalize the Hamiltonian. Which means I can compute any correlation I want. Because any correlation will be expressed in terms of phi and pi, which are expressed in terms of A and A dagger, which are expressed in terms of an harmonic oscillator Hamiltonian. So now I can compute everything I want. So again, this is the complete solution. It just happens that the energy is matching the Bogoliubov solution in a higher dimension. But as you will see, the physical properties, the observables, are completely different. So this is something which is interesting, but again, I want to emphasize here, this is the full solution of the Hamiltonian if you give me my approximations. Gesundheit. And you see, I could even compute exactly the coefficients that I have to put in my Hamiltonian as a function of the interaction, as a function of the density, and so on. So let me write the generic solution. So if I confine myself to the low energy part of the spectrum, why should I restrict myself to small k? Well, I did a lot of approximation that were assuming that phi is a smooth and slowly varying function. If I climb too high in k, this will be wrong. Clearly, the high values of k here are completely out of the scope of these approximations. Because high value of k means phi k in real space, phi of x would oscillate very fast with x. So I have to restrict this thing to k smaller than a certain cutoff of the order of 1 over a. Otherwise, I put harmonics in phi, which are too fast for the assumptions that I made in deriving this formula. So here I have to cut with a certain cutoff, which is of the order of 1 over a. And it means that I can describe properties at large distance, at long time, but I cannot describe properties at short distance. Like with any field theory, you sacrifice usually the short distance behavior to have a simplified theory, like any hydrodynamic description or whatever, to have a simplified theory that allows to describe things at large distance, but of course, much more simply. So here is the same. So let me put the cutoff so that I am below the change of regime to go to quartic. Then I can even simplify my Hamiltonian because I can neglect the k to the 4 compared to k to the 2. And then my Hamiltonian can be written in that way, sum over 2 pi, sum over dx, u times big K pi phi square, plus u over k, and I will explain what I mean to write here. These are this term and this term. And I just reparameterize these terms by two numbers, which I call u and k. And so with my derivation, u times k is nothing but rho 0. And u over k is nothing but g over 2 pi, probably. So this is the interaction. Why do I parameterize them that way? Because you can check that u as the dimensions of a velocity and k is dimensionless. I have two coefficients in the Hamiltonian, this one and this one, the coefficient of pi square, and I have the coefficient of grad phi square, so I can always reparameterize them. The reason why I did this is because then I can write that the energy is simply U times K. Okay, so this is the proper coefficient which enters into the spectrum. This is the slope of the energy. And K is a number which has no dimensions, okay? Which depends, of course, on the interactions. Now, this is a very nice solution, but we need to explore now its physics in more details, because, again, now I have this solution, but I have also the dictionary that we were discussing before, which is that the density, rho of x, is rho 0 minus 1 over pi grad phi sum over p of exponential of I 2p times pi rho 0x minus 2 phi of x. And we have the fact that the boson operator, B of x, is rho of x to the 1/2 times exponential of I theta of x. So now I can compute the correlation. Yeah. Yeah, so I probably forgot something. Yes, I forgot something. It was the 1 over 2m in the kinetic energy. You're absolutely correct. In the kinetic energy, there was a 2m here and a 2m there, and so on. Okay, so you can propagate. But trust me, at the end, U has the dimension of a velocity and K is dimensionless. You will see why in a second. So this works. But you're right. I forgot in all the previous thing, in the kinetic energy, I forgot the 2m. Yes. And of course, there are H bar floating everywhere, which gives the. So that's. Yeah. So at the end, this is correct in dimension. So that's why I go back to this simplified form, because there I'm sure of all the dimensions and all the things. There was another question. Yes. Yeah. So I get rid of the k to the 4th term because I'm saying I will only look at properties at large enough distance, so that at the end I'm interested in k values which are small enough so that the second term is negligible compared to the first. And of course this will depend on the interaction. So if the interactions are quite strong, I can go quite large in k. If the interactions are super small, it means that all what I'm saying will only apply to very large distance. But at intermediate distance, I wouldn't need to remember this term. So I could take it into account, but it's more complicated. So let me just throw it away and say at the end of the day, I'm only interested in very large distance correlations and whatever, which large distance means small k if you think in Fourier space, and therefore I throw away this term. But for bosons, this is indeed a cutoff which is interaction dependent, and the weaker the interaction will be, the lower the energy at which these approximations are valid will be correct. Are there other questions on this? Okay, so let's look at the physical properties. The first thing is there a superfluid? What is the average of B of x? Well, this is roughly the average of rho 0 to the 1/2, average of exponential of I theta of x. And now I told you this is something which is linear in harmonic oscillator. So this is something like sum over k, ak plus a dagger k, blah, blah. And this is the ground state of an harmonic oscillator. And there is, in that case, a property which is very nice, which is the average of something which is a linear sum of a and a dagger is equal to exponential of 1/2 of the average of whatever was in the exponential square. Again, this is a formula which is not totally obvious to prove. There are various ways. So either you expand the exponential to all orders, you compute the average, you resum, you re-exponentiate. That's a little bit painful. Much more simply, you go through path integral, and then that's just Gaussian integrals and completing a square. It's like computing the integral of exponential of minus ax squared plus by. you immediately see that this will give you something which is proportional to exponential of minus b squared times some constant here. So at the end, you can show this. Well, you can work out the solution, and you find 0. And because of the I, this is essentially exponential of minus 1/2 of the average of theta square of x. And the I gives you the minus sign. So this means that the fluctuations of theta are infinite. Theta is fluctuating all over the place. And therefore, contrarily to a higher dimensional system where essentially these fluctuations are small, theta is essentially 0, it's essentially a constant. In 1D, theta can fluctuate as much as it wants, and the fact that it fluctuates as much as it wants means that the average of this is 0. Exactly similar to what happened to the 2D XY model, where you have a spin which can point in one direction, but it fluctuates in direction so much by thermal fluctuation that the average is 0. So here we have no superfluid. Again, it doesn't mean we don't have a linear dispersion and a Bogoliubov spectrum. We have no superfluid, but still we have a very nice linear energy momentum relation. So what do we have? Let's compute the correlation, and there I just give you the results. I won't derive them. It takes a little bit of time to derive them. So let me give you the correlation where I create a boson at point 0, and I try to destroy it at point x. You can do the same thing by, of course, time dependent. It's not a big problem to do time dependent. It's also not a big problem to do finite temperature, but everything I'll say is restricted to finite temperature. This is proportional to 1 over x to the power 1 over 2k. And if I look at the density fluctuation, so delta rho of x, delta rho of 0, so again, I am creating some density disturbance at point 0, and I try to look how it propagates at point x. Then I will have two contributions. One is coming from the grad phi part. This part is behaving as 1 over x squared, and there is a constant here, there is a constant there. But I've also the density, which is nearly a periodic function. So let me just write the first oscillating term, p equal 1. If phi was a strict constant, the density will be totally periodic. So if I say I have a maximum of density at point 0, and I move to point x, I would just see the cosine. So I should just see something which would be cosine 2 pi rho 0 times x. But actually phi fluctuates, so it dephase if you want. It blurs, and the way it blurs is because it's traduced by the fact that it decreases as a power law of the distance, this time with an exponent 2k. And you can go further. Of course, there are the higher harmonic. You could write a cosine 4 pi rho 0 times x, and this time it decreases with an exponent which would be 8k, and so on, and so forth. So you see that this is very strange behavior. This is a behavior where the system doesn't know whether it should be a superfluid. A superfluid should be, this doesn't decrease at all. The phase is constant, so at the end, this goes to the square of b, which is non-zero in a superfluid. But here it decreases with distance, so I lose the phase coherence. But I lose it very slowly as a power law, and you see that the larger k is, the better it is. What does it mean, the larger k is? I can obtain k by dividing this relation by this relation, and you find immediately that k is proportional to 1 over square root of the interaction. So the weaker the interaction will be, the better my system will be a superfluid. Well, superfluid in the sense of BB dagger doesn't decrease. Keep in mind that again this theory becomes less and less applicable because I have to go down to lower and lower energy. On the other hand, if I look at density fluctuations, if this was not decreasing at all, what would I say? I would say I have a perfect crystal of bosons. And this will happen when K becomes very small. When K becomes very small, my density is perfectly oscillating. And if I add all the harmonics, I will get perfect delta peaks, exactly spaced. This is a crystal. So it tells that when K tends to 0, my bosons would like to be a crystal. K tending to 0 means interaction tending to infinity. Okay? And in a way, it's reasonable, no? I mean, you would say if the interactions are weak, but not too weak, otherwise I lose the spectrum, it becomes K square. I have a superfluid. If I put a super repulsion between the bosons, well, maybe they crystallize. It's weird, because it means that it's a system which doesn't know which order it has to select. Everything is decaying as power laws, and if you remember your critical phenomena, normally you find power law only at one magic temperature, which is the critical point. Everything decreases exponentially above and below Tc. Here, the system seems to be always in a critical state. It's always sort of hesitating. Should I be a superfluid? Should I be a crystal? And because I cannot know how to choose, I have quasi-long-range order in both. But sort of the nature of the quasi-long-range order is totally controlled by this parameter K. So this is a very weird situation where you get something which has quasi-long-range order, both in superfluid and in density. So let's say crystal. And which one is the best depends on K. You see that the change occurs when K is equal to 1/2. When K is equal to 1/2, this will decrease faster than this one. When K is larger than 1/2, this is decaying the more slowly, so you could say it's more superfluid than crystal. And when K is smaller than 1/2, this is decreasing the more slowly, so you could say it's more crystalline than superfluid. But in any case, it's power laws. Okay, so it's a weird situation. It's something that usually does not exist in high dimensions. In high dimension, the system chooses. I become a crystal, or I become a superfluid. But once I've done this, that's it. All the other orders are suppressed exponentially. Here in 1D, the system is dancing from one foot to the other and doesn't really know what to choose. So I can write for you a phase diagram if you want. It's not a phase diagram. It's just to say which one is the more slowly decreasing correlation. And if I take this criterion, you see that you would get as a function of K. So here K would be infinity. I put 1 as a reference point. And then I would have 1/2. So I would say here mostly superfluid. And here I would say mostly crystal. Sometimes it's called charge density wave because okay, you get a wave which describes the density. More importantly, we see that we have computed something remarkable. We know exactly the correlations. They are power laws. So what are the Fourier transform? The Fourier transform of the first one is the n of K, the momentum distribution. So what is the Fourier transform of a power law? So if I wanted to compute n of K, the momentum distribution, I would simply do the sum over dx of exponential of ikx and then the Fourier transform of this one. Now, this is behaving as 1 over x to power 1 over 2k. Now, by dimensional analysis, this is behaving as x to the power 1 minus 1 over 2k. And by dimensional analysis, x is 1 over k. So this is a power law of k, which is behaving as k to the power 1 over 2k minus 1. So I don't get a delta function at the origin, like in a real Bose condensate. If I had a BEC, so n of k, if I had a BEC, then I would expect a delta function at the origin, delta of k, with a certain constant, alpha, and then some background here, which I don't care. Here, I don't get the delta function peak, but I get something which tells me I would so much like to have a delta function peak at the origin, but I can't because I'm prevented by the Mermin-Wagner theorem to order. And so the system in 1D is doing a power law around the origin. It diverges. If k is small enough, it diverges. And this is the 1D bosons. At k equal 1/2, it doesn't diverge anymore, but for small k, let's say, it still diverge, and that's the signature of what people call quasi-long-range order. Sorry? At large k, sorry, I said small k, large k, of course. Small interactions, large k. Okay? So the density is a little bit more subtle. So let me show you the result. I won't derive it. But what can I expect there? I can expect that for wave vectors, which are 2 pi rho 0 x, I will also get divergence. So I won't only get divergence at k equals 0, but I will get divergence also at k equal pi 0, 2 pi rho 0. Now, rather than do the Fourier transform or show you the Fourier transform just in space, let me assume that I've done the correlation both in space and time, so that I have computed the fluctuation where I create a disturbance at point 0 time 0, and I measure it at point x and time t, which allows me to do the Fourier transform in momentum and frequency. And this is what people call the structure factor. And I will give you the structure factor both for Bogolyubov and for 1D. And so for Bogolyubov, that's very simple. When you do this, you get a resonance when the energy is equal to the excitation you can create. The excitation you can create is epsilon k, what we were saying before. So you will kind of get a lot of intensity here on the spectrum. So if you want, it's a color code, black and white color code, where when I draw something dense here, it means I have a peak, which means the Fourier transform is very large. When I don't write anything, it's 0, if you want. This is what you would get for BEC with Bogolyubov. Now, what do you get in 1D? Well, you will get this, but a little bit more complicated, because you get this around q equals 0. And if you remember, around q equals 0, we had this spectrum, which is roughly linear. So you will get something which it looks the same at the beginning, but there is something at 2 pi rho 0 here, which has also power law, so there is a lot of intensity around here. At the end, it gives something like this. Intensity is not constant everywhere, but you get a lot of intensity here. But then the system remembers it would like also to be a crystal. So it tells you if I do the Fourier transform, I also get a lot of intensity around that point. So this is very different to look at. Yeah. For k, you mean smaller than 1/2? Yeah. Okay, so the reason is the following, if I can find my correlation function back. So let me compare the decay of the density-density correlations and the decay of the superfluid. If k is 0, you see that the superfluid correlation, they decay super fast. On the contrary, this part here doesn't decay at all. Yeah, but this one decays, that's okay. But this is a smooth part. But this part, which oscillates with frequency 2 pi rho 0 x, doesn't decay. So it means that if I look at the density and say I have a maximum at that point, I can go 10 kilometers away and find exactly the position of all the maxima. Which means that's what you get in a crystal. And that's the same for all the harmonics. So at the end, you will get a perfect crystal. So if K was 0, you would get a perfect crystal. And again, the part which decays is the fact that you would distort this crystal by compressing it or expanding it. And the fact that it decreased tells you you don't even do that. So you really put the particles in an ordered state. Yeah.
But in a real crystal, we wouldn't have the B over X squared, right?
In a real crystal, you would have something like this also, because a real crystal still has little fluctuations, which corresponds to possibility to compress or expand elastically around the perfect positions. Of course, if the crystal is completely frozen, this term would just go away. But in an harmonic crystal, if you compute the effect of phonons, that's exactly what you would get. Yeah.
Why you make this strong difference in the crystal phase or K is low?
No, it's just, I shouldn't make a strong difference. I'm just saying, if you want to visualize your system, you might think more of the system as a superfluid from there to there, or as a crystal from there to there, but it has both characteristics. So I shouldn't make it. It's just as a convenience. Okay, so that's a very good question. People have put forward the term super solid to give the name of something which is superfluid and a solid. Now, by this naive thing, you would say this is a super solid. But I don't like this denomination of super solid unless you say I have perfect order in one and maybe quasi-long range order in the other. So I think technically a super solid should be I get perfect order in superfluidity. So average of B would be non-zero, but I also get power law in the solid fluctuations, or I get perfect order in the crystal, and I get power law in the superfluid. In that sense, this is not a super solid. So it depends which definition of super solid you take. It's something which has tendency to become a solid and tendency to become a superfluid. That's definitely true. But again, I think for super solid, one should ask more. One should ask that one of the order is perfect, while the other is at least a power law. And that, whether it exists or not, is a different story. Are there other questions on this? Okay, so that's the physical properties that one get. Let me, yeah. Yeah. So here, well, here in a way, if the interactions are finite, none of the order is ever perfect. Neither the superfluid nor the density. They all decay. And the reason is that you cannot break a continuous symmetry. So the superfluid order cannot break the phase symmetry of the wave function. And the crystal cannot break the continuous translational symmetry of the problem. So this is a case where you're kind of prevented from ordering, because you're in 1D, both in crystal order and in superfluid order. Is it okay? Okay, so let me just show you for completeness the structure factor computed by a more exact technique, which is the Bethe-Ansatz, actually. There was a breakthrough recently, people from, this should be an omega for some reason. There was a breakthrough in Bethe-Ansatz, and people managed to compute the correlation function, because you have to realize that when people tell you with Bethe-Ansatz we know that the model is exactly solvable, usually that's all they know. But they have no clue about the solution. Then they work 20 years and they give you the spectrum for a finite size model. Then they work 20 more years and they give you the thermodynamics. And then they work 40 more years and they can give you the correlations. For the moment, it has been done for two models. It has been done for this model, the Luttinger model, and it has been done for the spin chain, the Heisenberg model. But that's a very good benchmark of all the field theory. I was going to say bullshit, but all the field theory that I told you, to see if we reproduce what is the exact solution. Because believe me, the exact solution here, it costs you more than 5 lines or 1 hour of lectures to do. And this is as a function of the interaction. Whoops, here it is. This is as a function of the interaction here. Gamma is the ratio of interaction, so it's G divided by kinetic energy. So this is growing. And you see that if the interaction is super small, you kind of see the Bogoliubov part in the structure factor. So you see only the intensity around Q equals 0. What they call Kf is what I call 2 pi rho 0. Why it's called Kf, we'll come back to that later. Okay. And so it means maybe there is something there, but it's invisible. You don't see it. The spectral weight is too small. But as you crank up the interaction, there is no dispute that you see exactly what was the field theory solution. So you see that you get low energy modes, which are here, but you also get low energy modes, which are around this point, as predicted by the field theory, which tells you that the system has long wavelength fluctuations, but it has also a very strong tendency to have crystalline order with 2 pi rho 0. Sorry? Oh, because the image has been screwed up. You mean this one? This? This is a defect in the image. I think it's not, I mean, or a defect in the way they did their plot. There is, I don't think there is a reason why there should be a strong singularity there. Maybe there is, but at least I don't know what would be the reason there. Unless something magic linked with 2KF. No, so maybe there is a good reason. That's a good question. I don't know. What is this? I should check back whether there is a good reason why there should be a little king, because indeed it seems to occur always at the magic value 2. Here. For gamma equal infinity, as we will rediscuss, this is a free fermion theory. So there we can answer the question very rapidly. Yeah. Yeah, so that's why I'm not sure it's, what I mean is that maybe it's real, maybe it's an artifact of the plot, but here, at least if it's real, I don't know the answer. That's the okay, so let's stop here for the thing I wanted to tell you on the solution. Now, of course, you could complain that I derived this solution with. So let me skip the other system. So I because of time. Oops. Okay. Because of time, I won't have time to do for you the same derivation for spins. The screen is frozen. Because I think this thing has decided that I should continue the presentation. Yes. Okay, so I won't do the derivation for you for, sorry, yes. Yeah. So here, the field theory is only giving you the low energy part of the spectrum. So you shouldn't trust it here. So rather, when I drew that, I was abusing my solution. What I should have told you is that the only part of what I'm drawing you should look at is actually this one. So the thing which is in the box here. Low energy, around here, around there, around there, around there. And this part is beyond the reach of the field theory. And we'll discuss in a moment how to reach this part. So you could be very happy because on one hand you get things which seem to work very well in comparison to much more complex solution. On the other hand, you could be completely unhappy with the derivation. And let me just mention that you can do a similar derivation for spins and fermions, and it goes exactly along the same lines. I will just tell you how you can go from fermions to bosons. I won't do the derivation, but it's very simple. Bosons, the operator B of x, B of x prime, B dagger of x prime, they commute. If you add fermion operator, C of x, C dagger of x prime, it's the anti-commutator which has a delta function. Okay? So now, the density of bosons or fermions, it's the same. I can follow the same procedure. So if I have the rho C, I can do the same decomposition. But now, I cannot just write that the density is square root of C dagger C, because if I do this, I will get the commutation relation. if I want to impose the same relation between phi and theta, or I have to change the relation between phi and theta. But if I don't want to do that, I just have to twist this commutation relation to put a minus sign somewhere. And you can do that by adding a phase. And so I pretend that if I write that C of x is B of x times exponential of high 1/2 of phi L of x, it does the trick. So by just adding this field here, you can inject now this expression, and you will find that the anti-commutator works with the same relation between phi and theta. It's called a Jordan-Wigner transformation. This was invented for the first time by Jordan and Wigner to go from spins to fermions. And this is a trick that works very well in 1D. And you see that this is a transformation which is non-local. So you have to beware that this is an operator which depends on point x. This is an operator, of course, which depends on point x. This looks like an operator which depends only on point x. But actually, if you remember what phi L is, phi L of x is 2 pi rho 0 x minus 2 phi of x. And if you remember, we had the relation that rho of x was essentially minus 1 over pi grad phi. So actually, this thing is essentially 2 over pi integral from minus infinity to x of dy rho of y. So this is a whole string which depends on the density up to the point where I'm doing the measurement. So this is a highly non-local transformation. But using this highly non-local transformation, you can transmute fermions into bosons, or bosons into fermions, or bosons into spins, or spins into fermions, and whatever you want. And again, this is something that works well in 1D, because in 1D, you go from the left, and you reach your point. If you're in 2D, what do you do? There is no left of the point. So this transformation, they work very well in 1D, and you can use and abuse them. And using this, you can follow exactly the same prescription for the fermions. But I won't do it, because otherwise we won't get lunch. So I just want to give you the sort of punchline, which is now the concept of something called the Tomonaga Luttinger liquid. So the name was coined by Duncan Haldane, just like the Fermi liquid has been invented by Landau, and is not called the Landau liquid, but should. The Tomonaga Luttinger liquid has been invented by Haldane, and is not called the Haldane liquid, but it should. And but the name is very nice. It recognizes early contribution in the field, so it's stuck, and it's good name. And this is the following idea. This is the universality of the solution. So the idea is the following. You could say what is correct in what I did and what is wrong in what I did. The answer is everything I did is correct. If I consider that my Hamiltonian is 1 over 2 pi sum over dx u times k pi phi square plus u over k grad phi square, and that b is square root of rho to the 1/2 exponential of plus I theta, and rho is equal to rho 0 minus blah blah. I won't write it again. So this gives exactly up to amplitudes, meaning I cannot guarantee that I will get the coefficients here right. A, B, C, D, these are free, okay? Because they depend on the ultraviolet structure of the theory. You see that here, if I make x go to 0, this has no meaning. So this thing depends on the precise microscopic detail of the theory, so I cannot get it out of a field theory. I have to know the precise microscopic model. So the amplitudes are unknown. That might be a problem, but they are known. Okay. And of course, I'm up to amplitudes, the asymptotic, meaning large scale, large space, and time, or time, correlations. But there is a price. The thing which is wrong is what I did here. I gave you an explicit expression for the coefficients here. This is obtained by a perturbative expansion in interaction. And what will happen is that if the interaction is not very small, all the other terms, they are irrelevant. They don't change the nature of the Hamiltonian, but they change these terms. So in other words, these terms have to be put exactly, but then once I've done this, I can compute all the correlation functions I want, and I will get them exactly. Now the question you could say is how to get these terms exactly. So it's a little bit like Fermi liquid. You have a mass, which is the effective mass. This you can compute perturbatively in interaction, but the range of validity of Fermi liquid is much bigger than perturbation theory. We know systems for which the mass is 1,000 times the bare mass of the electron. No way you get that by perturbation theory. Nevertheless, all the structure of the theory works. Same thing with Luttinger liquid. I can take a G which is 10 million, then my little perturbation theory in G will be completely wrong. I have to remember all the irrelevant operators. But at the end, the only thing that will happen is that this formula will be modified in a complicated way, but I still have my two parameters, period. It's just that the dependence of K and U in interaction is not given by this formula. So if I have a trick to compute these parameters, so provided that one uses the exact values of U and K. So if G is small, perturbation is a good approximation. Otherwise, how do I do? How do I get this value? I have two parameters. I can do it many ways. I do two experiments. I measure the correlation on two experiments. I get my two parameters. And then I can fit all the other experiments. So it has predictive power. I extract these parameters from two experiments. But that's it. Once I fix these two numbers, I have two numbers. And I can compute everything, the time dependence, the temperature dependence, the K dependence, the frequency dependence of any correlation. Already the fact that, for example, the exponents here of the various harmonics are with a fixed relation, it's a non-trivial prediction. It's not an arbitrary exponent here, an arbitrary exponent there, an arbitrary. It depends on the same number. The fact that this exponent is exactly the inverse of this one, it's a prediction. But you can do better. It controls everything. So I can even extract these parameters from thermodynamic quantities, the specific heat. So the idea is to extract them where you can. And essentially where you can means exact solutions. Smart IDs. And more importantly, numerics. Why? Because you can use things that either numerics or exact solution are able to give you reliably. It's very difficult in numerics to give you the large distance behavior of a correlation function. You compute on 100 sites. So that's a nightmare. But to give you the compressibility of a system, It's very easy because it's a thermodynamic quantity. So the numerical error is very small. And it just happened that the compressibility is U over K. The specific heat is T over U. The size dependence of the energy minus the energy at infinite size is varying proportionally to U divided by L square. So you can use all these relations. There are plenty of relations like this. You just need to. You get the exponent perfectly out of these relations, and then you can compute things that the numerics is not so good as computing, like very large distance behavior of correlation functions, time dependence of correlation functions, real time dependence of correlation functions. So this has turned into a super efficient tool. Same thing with Bethe-Ansatz. I told you they need to work 20 years to get the thermodynamics, but at least they get the thermodynamics. So you use these relations from Bethe-Ansatz, you extract the exact value of the parameters. And then you inject them in the correlation functions, and you can compute correlation for model for which they cannot yet compute the correlation functions directly. So this has proven to be a fantastic way to solve essentially exactly models by combining different techniques, by combining the numerics at distances for which the numeric is strong with the field theory for properties for which the field theory is strong. And as a result, we get a very complete solution of the 1D problem, at least in simple case. And let me just show you one example. Actually, we can even compute also the amplitudes now. But let me just give you an example because time is running short. So I'll go back. Let me just show you a couple of phases first, because I think it's always nice. Check. So again, initially this is a field that started with standard many-body theory. So this is Tomonaga, Luttinger, Gorkov, Dialoginski, and Larkin, who did absolutely pioneering work, but they did it with standard many-body theory, so Feynman diagrams and whatever. And this is really hitting your head on the wall because you need to be an extremely high-powered theorist to use standard, the original basis to solve the problem. Then, as we mentioned, there is exact solution. This is Hans Bethe and Elliott Lieb. They are the Bethe-Ansatz solution. And this is definitely a field where using this exact solution has proven extremely useful. And then there is the field theory, and the main player there, where in the 70s, Alan Luther and the late Vic Emery, who set the stage for this bosonization technique that I told you. And then, as I said, Duncan Haldane, who understood that all these things which people thought approximative solutions, because you throw this and you throw that. For fermions, people said we expand around the solution with a strict linear spectrum, but what about the curvature? And blah, blah, blah. And what Haldane understood is that this Hamiltonian is a fixed point in the renormalization sense. All the rest is irrelevant. You can throw it away, but you need to put the exact parameter in it. And once you've done that, you get the exact solution. And that's the beauty of it. So numerics did also humongous progress. There is a beautiful method developed by Steve White, which is called the DMRG, the density matrix renormalization group, that I don't have time to discuss. And the beauty of the field is that you can make these three things work together, and things that can be computed efficiently by this technique, like the high part of the spectrum, the high part of the S of Q. High energy means short time, short distance. Numerics gives you this, but it cannot give you the bottom. No problem. You switch on the field theory, and you just inject the right parameters, and you get the full description. So this is a field where these three branches have learned to work together, and I'm sure if we could do that in higher dimension, there would be tremendous progress. The difficulty is that we don't have good overlap between the field theory and the numerics. Okay, so this is what I told you. I put it in the slides so you can get it. So this is the thing. You can do finite temperature. One can do spins. I just indicated the fermions. This is what I just told you directly. And let me skip that. Doesn't matter at that stage. Let me just show you a couple of examples. So here is what was measured in the frequency-dependent conductivity of organic conductors. And you see very clearly Paolo's behavior of the frequency-dependent conductivity, which is the signature of this Luttinger liquid type behavior, which is power laws that one expects in 1D. Same thing for carbon nanotubes. Okay, there is a little debate on this data, so let me not go too much in detail, but the conductance of the problem shows again a power law of the temperature in agreement with what you would expect here. Let me skip the spin chains and ladders, and let's go to cold atoms. So people try to observe this weird 1D properties, and there is a very early experiment by Dave Weiss where he tried to check whether, well, not tried, he succeeded in checking that if you put infinite repulsion between bosons, at the end, two bosons cannot be at the same place. Means they are fermions. Pauli principle is enforced by the interactions, if you want, not by Pauli statistics. And if I say I have a bosonic wave function which has nodes, every time there is another particle, I can say every time I have a node, I reverse the sign of the wave function. Doesn't change anything for quantities which are the square of the wave function, like the density, but this is a fermionic solution. So at infinite repulsion between bosons in 1D, I can map this problem exactly to free spinless fermions. And that's something that can be checked. And it's called the Tonks limit. And actually, all the formulas that I've showed you tell that this is true. Remember, the density of fermions in terms of phi and theta is the same than the density of bosons in terms of phi and theta. And you can check that. Very recent, very old experiment also in the group of Emmanuel Bloch, where he realized this Tonks gas, but he tried to measure the n of k. And normally, this is exactly what I showed you before. It should be a beautiful power law. So here is the fit with the power law. Yuck, horrible. Why? The trap. The trap, which makes the density vary from point to point, from tube to tube. So this thing is horrible. But you can fit it to theory, because the theory is a free fermions if the interaction is really infinite. But one would need a box to really check that there is a beautiful power law, and it's very difficult to check with the trap. So this shows difficulties with the trap. To try to avoid this problem, there were experiments in atom chips by the group of Jörg Schmidt-Meyer, and the theory was done by the late Iman Bekov and the Eugene's group. So again, measuring here an interference pattern, which is this function, then gives you something which you can interpret in terms of the Luttinger liquid. But the problem is because K is very large in these systems, it's the range, means interactions are very small. The range of applicability of the Luttinger theory is a little bit limited. More recently, there was a nice measurement which was done in Randy Hewlett group using Bragg spectroscopy, and the theory was made by Piotr Grisin, so we helped a little bit with the theory. So this is the measurement of the structure factor. So this is the Q equals 0 part. So this is the measurement. This is with fermions. So this is the measurement of this part by Bragg spectroscopy. So you measure here whether there is intensity, and then you measure the velocity u as a function of the interaction. And because we know very well the microscopic model, one can in principle compute what this velocity is exactly and check whether this Luttinger liquid theory is working. So here is the data. I won't go into the detail of Bragg spectroscopy. And here is the comparison of the measured velocity with respect to the theory. So it works very well, and to the best of my knowledge, this was the first time that the interaction dependence of this velocity could be measured with good reliability. Just to show you how much I hate the trap. No. So people were happy about this. Here is the theory curve of what one has if you just have one tube. This is one tube. The square box is T equals 0. The finite box, the shape here is finite temperature. Here is the velocity. Here is the peak. And then you see how it goes. When you start putting all the tubes, it shifts here. So if you don't have a good way to do the theory from the start and take this effect into account and just try to extract the velocity directly by measuring the peak in the experiment, you get it completely wrong. And this is the effect of the trap. So if instead the experiment could have been done in a box, you don't need a theorist. You just look at that and say, here is the velocity. And that would be much better. So I hope that you will implement boxes in all the experiments. Okay. So there is another effect that I didn't have time to chat about, and maybe I will skip it. Perhaps Nathan will talk about it, perhaps not. But there is the fact that in 1D the excitations are very weird because they are this collective excitation, and so they can fractionalize. You can have separation of part of the excitation and separation of another part in a way which would be normally impossible. So you can reach quantum numbers that are smaller than the minimum quantum number you would expect. For example, if I have a particle which carries charge and spin, you can break it and have an excitation which only takes the charge and an excitation which only takes the spin. And normally it's impossible, but in 1D you can. So this is called fractionalization, and let me skip that. These are things that called atoms, so this is called spin-charge separation, but I won't have time to discuss this. And so now one is at the stage where you get quantitative agreement with the prediction of the Luttinger liquid. So one question one should ask in that case is it the end of the story? Do you, I mean, that's it, finished, work on something else? And of course, this is completely wrong, because now that we have this firm theory to solve very nice translationally invariant, simple systems, we are in the same position than the people in the 50s were with the Fermi liquid theory. Now we have to invent superconductivity, we have to invent giant magnetoresistance, we have to invent all the rest, but we have a firm way to deal with the interactions. And so you are in a situation where by using this type of theory, but then putting perturbation, disorder, dynamics, a lattice, weird things, coupling between chains, now you move away from the Luttinger liquid, this simple theory, but at least this can take care of the main effect of the interactions, and the perturbation you're adding will give you new phenomena. So I won't go in details in all the examples. I've put a couple of examples here. One is the effect of a lattice. If you put a lattice, you know that systems can turn to superfluid to Mott insulator. Well, in 1D you know, or you can use Luttinger liquid theory to treat this problem, and it works very beautifully. There were experiments that, let me skip that, there were experiments that were done in the group of Hans-Christoph Nagel and in the group of Giovanni Modugno, where one has an excellent tool using Luttinger liquid to attack this issue. Let me again skip that. You can have good theoretical to measure topological, to stimulate the idea that there are topological orders, and there were some measurement. As I said, this object is actually, this field phi is actually a non-local field. So this is a weird thing, but you can measure it using microscopes, and there were already some, this is already an ancient reference, but there are more recent experiments in the group of Emmanuel Bloch where they measured string order parameters for fermions, and I'll skip that. You can do what you want, disorder, multi-component mixture. All this will take you away from Luttinger liquid, but of course, using the Luttinger liquid as a starting point to study this new physics. Transport, there is a poster which will tell you more on this, which is what is the transport through a 1D periodic structure and how a 1D periodic structure resists becoming superconductor. So I don't want to, you have a poster that you can look where this data is shown. And of course, one of the interesting questions is what happens if instead of having one 1D material, you start coupling these 1D systems, and how would you go from the weird physics of 1D to the more conventional maybe, or maybe not so much if it's high TC, conventional or unconventional physics in more than one dimension. And this is directly relevant in various situations, like a 1D system which is coupled to a 2D bath, a 1D system to which you send microwaves, for example, and then you change drastically the spectrum. And all these things we can touch barely, but there is a lot of open questions, both experimentally and theoretically. If you look at these organic conductors that I already showed you, which is made of many 1D chains. The bottom part of the phase diagram has a superconducting phase. Nobody knows what is causing this superconductivity. So in that way, it's like the high TC. We don't know what is the mechanism. This is in a regime of temperature where the material is 3D. So it certainly remembers that it had 1D physics, but it's not in the 1D regime anymore. And one must study it. And clearly cold atoms are a very good system to do this because you can control the tunneling between the chains. So increasing the tunneling between the chains can be much better done by tuning the barriers in cold atom system than applying pressure on a condensed matter system. So okay, let me skip that. Let me skip this also. There are many, many problems. I put a couple of reference. I, of course, cannot not show you a picture of the group and also mention the various people. There are many more that I cannot mention here, with whom we had fun playing with 1D systems. And I would conclude by saying what I just told you. This was just a tour of 1D physics. And the most important message is that now we have a framework to study this physics and, more importantly, go beyond. And there are challenging questions which require and which can be solved by an interplay of analytical and numerical technique. And what is the most important is that there are many, many experimental realizations. So it's not just theoretical fun. So I think it's a good world to explore. And on that, I'll stop and thank you for your attention. So are there questions? Everybody's hungry. Okay, no question.